according to the schedule, in theory, this is when I get it all in. I might have a couple little demos I want to show you, but I don't get to today. We'll see. But then we'll do that Friday when we review. But this is the big bulk one. Because then Friday's review. Monday is your exam on this light stuff. Then next Wednesday is the last day of classes. And we'll review everything. Look through. You have about a week now to see the stuff that confused you the most, for the whole semester. Or like, oh yeah, I remember that motion stuff, and I never did quite get this. Well, that's perfect time to bring that question. Otherwise, I'll just go over things. Clearly, I won't have time to go over every single thing. But you have the homework. And I still see that most of you haven't even looked at the solutions. Of course, the way I design the homework is usually you know what the correct answer is by the time you finish, if you keep guessing. But I have explanations there. Same with the tests. And honestly, those are your two best ways of reviewing, I think. That's all in the textbook. You got my lectures, but I doubt all of you are going to spend, how many hours rewatching every lecture. But maybe you can hit some key ones. If you haven't noticed yet, I put tags, keywords, at least on the topics that we were covering. So if you had a hard time with reflection, at least it's in the keyword, if that helps you figure it out. And there we have it. Okay. I messed up last time. It wasn't, you were probably like, yeah, so what? But it's bothering me, so here I'm redeeming myself while we review. Raindrop. Rainbows was kind of at the end. Light ray comes in, and you get reflection off that surface, and some of it refracts. But then you get reflection and refraction off of that interface. And let's see, it's going from water to air. So it'll speed up. So will it bend away or towards the normal? So it's coming like this. Well, we'll simplify here. Blown up. It's coming in. And this part starts going faster. This wheel starts going faster than this one, so it actually bends this way, away from the normal. So you'll get something like that. I'm drawing those smaller because that's not where most of the light goes. Most of it gets reflected there. Then the same idea here. And another one. Into your eyeball. That's all correct. What I got wrong was the reflection on the second one. If, and here's just some review, say that's the red light. Blue light, will it get bent more or less here? Yeah, it'll get bent more. Blue travels more slowly through the water. It's a higher frequency, so there's more interactions. So it'll get delayed a little bit longer. So it gets affected more. It's refracted a little bit more. This isn't drawn to scale, but so it might come to there. This is the one I drew wrong. If you follow the law of reflections, that would put it back on the other side. I had it down here last lecture. It's no biggie. You get violet or blue. But I had to correct myself because it's always been a pet peeve of mine when Hollywood or cereal boxes or Lucky Charms or anybody, when I see rainbows, what color's on the bottom of a rainbow? You got all the pretty colors. You know how I remember it? Which color gets refracted more? Blue. Which radius of these circles is the tightest? The bottom one is curved more. So yeah, you get blue down here. Red's up there on a primary rainbow. And so sometimes I see the pictures and they got it flipped, or the colors are completely out of order. And just internally, it's like, oh. I think, was it Little Mermaid at the end? I have to go watch it again. I think they did it backwards. You know, and I really liked the movie until that point. But no, I still watch it. But this is why, if this is coming into your eye, you can see that you trace this one back, red looks like it's coming from a spot that's higher up, where blue looks like it's somewhere lower. That's why. And again, you only see one color from one raindrop because this is way up in the sky and you're way over here, right? By the time these two rays diverge, only one color hits you from one raindrop. So if you see red from that raindrop, it's a different raindrop that's showing you the blue, and a different one for the green. Now they do have secondary rainbows. And your book draws this, but the idea is the light comes in down here, refracts, reflects, reflects again, and then refracts. And so you get two reflections, and that flips the order. So the secondary bow, the colors are flipped. But that's the dimmer, less common rainbow. But I think rainbows are cool because they work because of refraction and reflection. And because different colors travel different speeds through the medium because they're affected differently. I like that. Okay, I still want this. Lenses. If we have that was a convex lens. And do you remember what it does to incoming light rays? Do they come together or spread apart over here? And when you forget, you just play the law of reflection and refraction again. You know, if you blew that side up, and you got a light ray coming in, well, you draw your little normal. Get some reflected. And which way will it refract? From air into plastic, does it slow down? Or speed? It slows down. So this side's going to get slower. This side will go faster and it bends towards the normal. Then you get reflection here and refraction again. This time it bends away from the normal because it's speeding back up. And so actually this light ray will come this direction. And it's just based on the curvature here. One down here. Can you see it'll do the opposite? So it bends a little there, and it bends some here. And those will come together at some focal point. So this is a converging lens. They come together at some point. Some lenses, though, are not the perfect shape, like your eyeball. My eyeball is definitely not the perfect shape because I have an astigmatism. And what that means is it's a lens defect, if you will, or my cornea isn't shaped just like this. So light rays that come in everywhere should all come to this point if you're going to see sharply and in focus. That would be on your retina. So if that's your eyeball, whoops. That would be somebody that can see clearly. Well, if this isn't curved just right, maybe it's a little flatter here than it is over here, or it's more round there than it's supposed to be, then light rays that come in at different points have slightly different focal points. It might look something like this. So maybe you get one that comes in here, one that comes in there, and that's looking good, but maybe one out here crosses a little differently, and this one crosses there. Maybe you get another one. And this time, by not trying too hard, that's more accurate. They don't all seem to cross in exactly the same point. We call that an aberration. An aberration. It's a lens defect, and that causes a fuzzy image. Astigmatism is where my eyeball's not curved the same this way, or my cornea, as it is this way. And so light rays that come in one direction might come together, but light rays that come in this way might come together in a different spot. But your glasses can correct for that. It's an aberration. And how many of you have ever looked through telescopes or even microscopes or just anything with a lens, and the colors seem to have come out? You're looking at white light, and somehow on the fringes you start seeing a little red or a little blue. That's another type of aberration. The material here cannot, ideally, refract each color the same amount. That's why we get rainbows. And so the reds and the blues might not come together in the same spot because they have different wavelengths. They travel through here at different speeds, so they get bent different amounts, and the colors can get spread out slightly. And that's a chromatic aberration. And a lot of telescopes have to worry about that. They usually have another lens to kind of make it refract back the other way. So this one refracts it, and maybe they spread out, but the next one, through refraction, causes them to come back together to the same point, and you can correct for that. But so, a little review of reflection and refraction, some aberrations. Oh yeah, the other lens, concave, diverging. So that one will go straight through, but these, when you play the law of reflection and refraction, ends up spreading out. But you can have the same type of defects and whatnot, aberrations. Any questions? Oh heck, while I'm on it. This isn't in your book, but I like it. If your focal point is right here, then your eyeball's too strong. It focuses too quickly. And so by the time they come together, this is in focus, but they're blurry over here. This would be somebody like me that's nearsighted. Or your eyeball could just be a little too long. But you don't see clearly. That's nearsighted. What type of lenses do you think my glasses are? Do you think it's a convex lens or a concave lens? Converging or diverging? What do you put right here to move that focal point back to there? I heard a concave and a diverging, which is the same type. Yeah, if that is thinner in the middle, then it's going to spread them out before it enters your eyeball. So it'll take a little farther distance to come back together. Yeah. So you can look at somebody's glasses, and if they make the image smaller, you can tell it's thinner in the middle. Then you go, you have this type of lens. You must be nearsighted. Farsighted is the opposite. That would be where the focal point's here. It's not strong enough for the size of their eyeball. It takes longer to come together. So it needs help bringing it together, and you would give it that kind of lens for someone that's farsighted. So you look at their glasses, and that looks like a typical magnifying glass, right? So you look and you go, oh yeah, looks bigger. So you know you have this type of lens, you must be farsighted. It's good at party tricks. The last chapter, you actually know most of this from sound waves. It talks about diffraction. That's the new thing. We've mentioned it. But then it gets into superposition and interference of waves. We're just going to do it with light now. And with thin film interference, you get some different colors, holograms, and then there's a little bit on polarization. That is a new thing. So, diffraction. What the heck is diffraction? Let me show a demo and see if it works. So I have a slide with a slit in here, a spacing. Excuse me, that I'm shining light through. Let's focus that. With a lens, I'm just matching the focal point to the screen, pretty much. There, that's good enough. The edges are what I want you to notice. When light, which is a wave, you thought it was a wave, goes through that opening, things happen. Here, I've got the edges pretty sharp. What I'm going to do now is switch to a much smaller slit. I taped two razor blades together, really close together, so it's a really small opening. And let's see if the edges change any. It's a subtle effect. Let me dim the lights slightly, see if it makes it any more apparent. And what I'm hoping some of you can notice, front row maybe more in the back, these edges are fuzzier. I'll switch back for a comparison. In the back, maybe it looks sharp. But let me try to focus it. There-ish. That look pretty sharp. Now let's go switch back to the other one, the bigger opening. And now its edges, especially that left side, looks blurrier. When one's in focus, the other doesn't seem to be sharp. That's diffraction. When waves go past an edge, they can bend. It's not refraction. It's not changing mediums like from air to water. It's staying in the same medium, but it has an edge that's affecting it. And that's what I'm going to discuss now. So let's say you have an edge. And you have these waves coming at you. The arrows are the direction, the wave fronts you can think of. This works with sound waves, water waves, and light waves. You got these wave fronts coming at you. Well, what happens when it gets to here? What do you expect to see on this side? A shadow. I would expect some waves to continue like this. But this blocks them. Yeah, and if you had a screen here, you'd have a sharp edge right here. Well, that's not always what happens. Some of these waves bend around this corner. They start doing a little curvy thing. And so a wave that comes like here tends to get bent and curves over. And so over here on the screen, you get a little fuzzy region there. Partial shadow, if you will. And it makes the edges not look as sharp. That's diffraction, when waves bend around an edge. If you had two edges, and the waves came in, those will get squished through, and you'd have them out like this, but this one would start curving, and so would this one. And you essentially get like that. They start spreading out. That's diffraction, the spreading out of waves. Your book explains this. Oh, yes.
So when you play with the focus, are you trying to cancel out the diffraction? How does that help?
Yes, the projector uses a lens also. Just shining light through an opening or next to an edge is this, and this is the effect. I could make it sharper by changing the focal point of the lens and changing where these come together on the screen to appear sharper. But when one of them was sharp, say the big slit, then when I did the smaller slit, there was more diffraction. It was affected more. So it was even fuzzier. And the amount I corrected with the lens wasn't enough. Which is a good point. If this opening is smaller, like that, and you got the waves coming in, think of it. This wave is trying to fit through this little opening, so it's going to get affected more. There'll be more diffraction, and it'll spread out even more. It'll be a wider spread. An analogy is your garden hose. Water's coming out. What happens when you put your thumb over the end? It starts spraying. That's your analogy to help you remember. The smaller the opening you're trying to cram it through, the more it's going to diffract and spread out. You still have a question?
Yeah. So the diffraction. So if you had the lens in front of that, so if you have that much diffraction.
Yes, say we put a lens here. You could correct for that. Is that what you're getting at? This is spreading it out. That could bring it back together.
Yeah, what I was going to mention, that with the diffracted waves, they'll reflect the lens. Will they reflect the lens itself?
Will they reflect the lens itself? Do you mean are waves diffracted as they go through a lens?
No. No, so like the slide that you put in, and then there's some diffraction going on, and so the waves that are diffracted reflect on the lens after? And does that cause the fuzziness? And so then you change the focus point to correct that and bring it back together?
I have to double check if you're using the right, mean to use the right term. You're saying do they reflect after that? There's nothing to reflect off of. Some of the waves reflect off the front of the lens. They refract through the lens.
So, but it's sounding like there's a leak, kind of? It feels like a leak as it goes.
Yeah, you can definitely think of diffraction as a leak. Yes. You got a little opening here. A lot of people would think that this is the only place light would make it. You know, if you just have a light bulb, it emits light in all directions. But if you put like an opening right here with just a little hole, you don't get a nice straight parallel beam forever. It spreads out. In the opening, there's always a diffraction, this bending of waves as it goes past those edges. And the smaller that opening, the more it spreads out. So another thing to think of is the color. If you have a big wave, little opening, he gets affected more. So the color, the frequency, the wavelength of light matters. Red light should get affected by that opening more than blue light. Blue light's waves are smaller, so it's like, this is how I think of it, they can fit through the hole less affected. With a big wave, it's like cramming it in. And so longer wavelengths will diffract more than shorter wavelengths. So the wavelength matters, and the size of the opening matters. If this was a bigger opening, red would not be affected as much, and there would be less diffraction for the red. And blue would probably hardly get diffracted at all. Let's show diffraction with a laser. So here's the laser shining through an opening. The opening's really big right now, so you don't see much diffraction. But it's a variable slit. I'm going to make the opening gradually smaller, smaller, smaller. And some of you in the front can probably start to see a spread of the green light. I'll keep going smaller, smaller. Can you see it spreading out? That's diffraction. Once that opening gets small compared to the wavelength of green light, then sure, we can notice it. If I even go smaller, it's even wider. Let's see. Yep, that's as bright as it gets. Well, now we get superposition and interference when waves try to add on top of each other. Because diffraction occurs at every edge, if you have an opening, you get diffraction off of this edge as well as off of the other edge. And each of those can create their own bending. And those waves can interfere, superimpose. And remember, if one crest is up while the other's up, if they hit the screen at the same time they're up, we'll see a bright spot because they'll constructively interfere and reinforce. But if they hit the screen when one is up and one is down, they can completely cancel each other out and you won't see light. So let me do this again. And I don't know if you can tell in the back, there are bright and dark spots. Right here in the middle, they both take the same path to the screen and they add up and it's bright. But can you in the back see some dark spots? Say something. Let's see. Easier to see? That's interference. The wave from one edge is interfering with the wave from the other edge. Where it's bright, they're constructively adding up. They're both up crests. And when the dark spots, they're canceling. I have another laser. This one has two slits that the light goes through. So you still see that general spreading, and then a dark spot, and then some bright spot, and then dark spot. But each of those bigger bright spots gets subdivided because you have more edges. There's more interference. And they're creating lots of constructive and destructive interference spots. Does that make sense? Yes, question in the back?
How would you make an actually particle instead of this experiment?
Well, historically, this was the main experiment. Young did this. It's called Young's double slit experiment, which you just see, as definitive proof that light's a wave. And that stuck for a long time. There's other experiments that came later that said, well, wait, this seems to make more sense if we think of light as a particle. And you get this whole particle wave, which one is it? There's a big debate. Now it's pretty much we say, it's both. And seriously, in physics, when you can explain the phenomena as a photon of light, a particle, like this packet of light energy, that'll describe it. Like the photoelectric effect makes it think of it as a particle. That was Albert Einstein. That's actually why he won the Nobel Prize. It was for the photoelectric effect, not for relativity. But this one can be explained with a wave. And interestingly enough, you can shoot particles at two slits and still get that same pattern. That threw people off a lot. Quantum mechanics, people still talk about it. It's like, wait a minute. Okay, let's slow the particles down. What if the particle only goes at the slit one at a time? Electrons. They're particles. We think of them as billiard balls, right? Well, if it goes through one slit, how can it interfere with itself over here? But it does. And that's been kind of some proof that even particles can be represented as waves. And waves can be represented as particles. And now we consider it as kind of like this wave-particle duality thing. It's like neither. It's kind of both somehow. It's really cool. And if you go and measure and watch which slit it goes through, oh, I know it went through this one, then somehow the interference pattern goes away. Because it's like, well, that's weird. It's quantum mechanics. We can discuss it more later, but yeah, it's fun. All right, let's close those before the interpreters blind themselves. Put the big screen down and show you this another way. I showed you this before back with sound waves for interference. We'll revisit it. So here's my slides, and you can think of this point down at the bottom as a slit, an opening. It comes out and diffracts like this. But what if you have two edges or two slits? You get interference. Get my laser pointer here. So light from this side diffracts and spreads out. But so does light from this point. And this one, if the crests are both up, you'll get a bright spot. Or here. Or here. But right here, one wave, one crest is up while the other's down, and they interfere destructively, and you get a dark spot. And that was the pattern you just saw on the screen. That's what the laser light was doing. Sound waves did the same thing when you heard the sound get louder or quieter in different spots. And if you spread the slits out farther apart, you get less diffraction. Do you see the fringe pattern in there? They're getting closer together. What I want you to realize is that means they're not being spread out as much. It's easier when you go the other way. Let's make the opening smaller. We should get more diffraction, correct? Because you're trying to cram it through a smaller opening. Let's move those edges or slits together. And you see what happens to the fringe pattern? The fringe pattern spreads out. That means there's more diffraction because the opening's smaller. All right, let's pretend like we got some red light. Here's the wavelengths of red. If they overlap like there-ish. Over here, you see, they both add up. They take different paths to the screen. But there, they're constructively interfering, and you'll get a bright spot. That was like the center spot in our pattern over there on that screen. But if they travel different spots to the screen, at that point, do you see how they're out of phase now? They're out of step. One's up while one's down. They destructively interfere, and you get a dark spot on the screen there. You go up further, and they're back in phase again. So you get bright, dark, bright, and the same thing happens on this side. So I'll go down and you can watch it change again. Out of phase, in phase. Out of phase, in phase. Now this is reminding me of my botany class in college. When we get to cell division, she would always have us shout out, and she'd make us to remember, and it's worked. When the cells would divide, the actual step for division, who remembers what that's called? They told us it was mitosis, the actual where they split. But, so we'd always have to shout out, mitosis! I don't know, that was making me think of this. In phase! Out of phase! In phase! Anyway. Let's get to an out of phase one here. There. This beam travels a certain length to get to the screen. This one travels a different length. This bottom one has traveled exactly 1/2 of a wavelength further. Can you see that? It's had to travel 1/2 of a wave further to get to that same point. That's why it's out of phase. So when you're half wavelengths off, you get destructive interference. Up at this point, now it's traveled exactly 1 wavelength further than the top ray. You with me? So this extra path length difference determines whether things are in or out of phase. So let's try another demo. You can get this pattern in lots of things in the world. Let's see. Laser light. I'm just spreading it out into a beam to reflect off of this. This is Newton's rings, they call it. There's a picture of it in your book. And we need to be darker, of course. Let's try this one. Can you see that in the back? Hello? Well, let's keep going then. There we go. We'll deal with that. These are two pieces of glass. One is flat, and the other is slightly curved, convex. And they're right up against each other. If one's curved and one's flat, in some places there's a little bit of air between the two pieces of glass. You with me? Right in the middle, they're touching. But the curved one starts getting farther away from the flat one as it gets out to the edges. What happens is it causes a thin film of air sandwiched between the two pieces of glass. Light can reflect off of one surface of the glass, but remember, some of the light refracts on through. That refracted through light can then reflect off another edge and then come back out. Those different rays that come back out have traveled different lengths, and so they can cause interference. What I want you to realize here, I'll draw it better on the board, what's going on. But you can see the fringe pattern here, the light and dark circles and bands. That's due to this interference of light waves being in and out of phase. You can determine the optical flatness of glass this way. Here is two flat pieces of glass, and I'm just squeezing them together. Let me reflect it back onto the screen. There we are. And you can see that fringe pattern. I'm going to squeeze the glasses together so there's less air in between. And watch what happens to the fringe pattern. You can change the spacing of the fringes because I'm changing the extra distance one of the light rays has to travel. Okay, let me turn the lights back on for us. This is hard to draw. I'm not going to do it the way. Let's do it with beams. It's drawn well in your book, of course. All right, we're going to call this glass and this glass. So two pieces of glass with air in between. And this is really thin, so not drawn to scale. If a light ray comes in, like my laser, it follows the law of reflection. And you get a reflected ray, you get a refracted ray, you get another reflected ray. The one I'm interested in is it'll come down to here. You'll get refraction in there and reflect back. And then, let's see, air to glass, refracts again, and comes back out. Okay. Point is, it has a fun path, but it comes in. This will do something too. Right here, it reflects. And if your eyeball's over here, you see the light. Well, this light's reflecting too. So is this one. And they've each traveled different path lengths. But the dominant ones are here and here. So this ray and this ray. Is that right? Here comes that one too. Whatever, you get the point. This, sorry about your notes. Try to keep it simple for you. Let's just look at these two. It'll be simpler. This ray has to travel into that point and back to your eye. This ray has traveled a little bit further, this much. If that extra distance allows this ray to get out of phase with this one, what will you see? I heard it. Destructive interference. If this travels exactly a half a wavelength or some multiple half wavelength, they'll be out of phase, and you'll see the dark spot. But over here, it's a little different distance, and so maybe they're in phase there. It's traveled some multiple whole integer of the wavelength. And then over here, the distance is a little off again, and you might see destructive. And that's how you get that interference pattern that we saw up there with the glass. And that fringe pattern tells you, in a sense, how thin that layer is. This layer of air right here. That has to be on the order of colors of light to have that effect. If this gets too big, you get all this scattering or whatnot. But it's more fun when you have colors. This was just green light only. And so it's either out of phase, dark spot. In phase, bright spot. So you saw green or you didn't. What if you hit it with white light? When green's out of phase, what would you see? What colors are left? What colors don't get destructively interfered? Red and blue, which combine to make magenta. Very good. So you would see right here, if green is being destroyed, you'd see magenta. Over here, let's say red is being out of phase. What would you see? Cyan, the blue and the green. Well, let's do that. That's soap bubbles. I got a soap bubble for you. Before I turn the lights off. This is full of bubble soap solution, and I'm going to dip that frame in there and form get a bubble in between it. So we'll have a screen, a plane of bubble, and then I'll reflect the light off of it and focus it onto the screen so we can all see what's going on, hopefully. And there it is. Move this for now. So the bubble is the thin film. It's like sandwiched between air on both sides. And so the light rays are going from air into the bubble solution. Some of the light reflects off the front surface of the bubble. Some of the light goes into the bubble and reflects off the backside and comes back out. The thickness of the bubble determines which wavelengths get in and out of phase. And you can see the complementary colors already, kind of the cyans, magentas, and greens. Green happens more than blue. You're starting to see blue here. But you can tell which wavelengths are getting destroyed. Let's see. See, there's the green. So in that thickness of the bubble, in that position, blue and red are being more destroyed, destructively out of phase. Here's a yellow. That's red and green. So blue wavelengths at that thickness must be getting out of phase. This, remember, the lens that's focusing onto the screen flips the image. So this is actually the top of the bubble. This is the bottom. So gravity's pulling the fluid that way. Pulling it down, but that moves it to the top of our image. And you can see the fringes are getting closer together up here, where the fluid is accumulating and getting thicker. At the top, it's thinner. And so that thin film is changing thickness throughout, and that's why you see these different colors. But it's the same thing on when you blow soap bubbles. Those colors you see, or oil on water. Sometimes somebody dropped grease and it gets rainy. It creates a thin film. And light that's reflecting off of a front surface is interfering with light that went into the film and reflected back out. In or out of phase. I think that's neat. I'll let that keep going. Here is another concept. A total internal reflection. It's called total internal reflection. When light goes from something where it's moving slower and tries to go to something that's moving faster, which way does it bend? Towards the normal or away? We're going from slower to faster. So that's like water back into air. Away from the normal. At some angle that you approach that interface with, the refracted ray can't move any further. It can get, if this is the normal, my arm, straight up, if you get refracted away from that normal, say like this, well, you can get refracted more. At some point, you're going back into the medium. And there's no longer any light that ever gets refracted out. All of the light, 100% of it, will get totally, internally reflected. So it can't escape. That's fiber optic cables. So like this little toy, it has a light in the base, and it shines through one end of the cable and gets, in a sense, trapped and bounces inside the cable, continually, totally internally reflecting until it comes out the little end and you see it. I can show that. Here's just a big rod. If I shine my laser straight up, you see it on the ceiling? Let's shine it through the rod. Can you see it inside the rod? How it bends? It comes out of funky patterns on the ceiling. Let me aim it this way. Can you see it totally internally reflecting inside the rod? They call this the critical angle. If the incident angle, the angle the light comes in at, is bigger than this critical angle, that refracted ray disappears. It's too steep, so to speak. And all of that light stays trapped and reflects back into the rod in this case. So this is like a crude fiber optic cable. I'm glad you asked. You can see it through the sides, can't you? So this is a lame fiber optic cable. If you can see the light coming out the sides, very good observation. Most people don't ask. Then some of the light is refracting through so you can see it. Mostly with this, it's because it scatters, because this is just plastic. True fiber optic cables like this trap more of the light. They're more efficient. Here's a different version. Just another rod. But you can see it brighter coming out the spot facing you. Because again, it's totally internally reflecting. And my favorite one is this side. Here's a cylinder, a shell of a cylinder. I'm going to put it inside because I've cut a little notch. And look what happens. It's totally internally reflected in the wall of the cylinder. It's trapped inside the wall and spirals down. From above, I can see it doing its little zigzag pattern. Totally internally reflecting. Well, that's cool. So it's a way to trap light, or at least guide it to where you want to go. Let's see, time's up. You guys have any questions? Okay. In chapter 29, it's useful how to consider these things. Hawkins' principle. It looks like Huygens. They talk about it in chapter 29. I didn't discuss it. It's useful, but I'm not holding you to it. Hawkins' principle. We'll review Friday, and I'll just mention what polarization and holograms are. But you have everything you need to understand it now. Have a good day.